As yeah, okay. So my name is Ben Kemke. I'm here with Papanudo, Brad Campbell, Prabal Dutta from the University of Michigan, and today I will be talking about our indoor RF localization system called SurePoint. And what SurePoint does is it exploits this concept of ultra-wideband flooding and diversity to provide robust, high-fidelity indoor localization. So SurePoint rides on the coattails of ultra-wideband localization, which has been shown in the past, and its ability to achieve high localization accuracy in indoor environments. So SurePoint itself, through experiments that we've run, we're able to achieve an average error of about 17 centimeters of 3D location, and 95% of location estimates are within 76 centimeters. And really, the SurePoint system is enabled through the advent of commercially available ultra-wideband technologies. The focus of the SurePoint system itself is on addressing a lot of the limitations that ultra-wideband presents, and they're specific to ultra-wideband in general, and in their application in the real world. So if we actually look at the history of RF-based techniques versus those which are either optical or acoustic, back about a decade ago, you really needed to concentrate on the media, such as the acoustic or the optical media, to achieve high accuracy in indoor environments. But as time has progressed, we've actually seen a large improvement in the localization accuracy, which is attainable through these sort of commodity scale localization platforms. And the reason for this, I had already alluded to, is the fact that these ultra-wideband technologies are now available in a commercially available, sub $10 price point for an integrated circuit. So why does ultra-wideband RF localization yield better localization performance? So if we actually take a simplified view of the indoor RF environment, ultra-wideband signals have a very tight time domain representation of the signal, and therefore in multipath environments you're able to actually separate out the line of sight path, which is the one that you're interested in when performing localization operations, from that of the secondary paths, which are longer in length from the transmitter to the receiver in the indoor environment. So you're able to more easily distinguish that first line of sight path. In the case of narrowband techniques, they do not achieve as high of accuracy because of the properties that these two paths will coalesce, and therefore you get a distortion of that time of arrival. So ultra-wideband itself has shown significant performance gains in terms of accuracy, but it comes at the cost of other limitations. In terms of robustness of the messages which are transmitted back and forth, there's a regulatory limited power of the transmit power level that you're able to attain because of the fact that these ultra-wideband technologies utilize, might overlap with their narrowband counterparts. And issues of scalability also are interesting and have not been addressed in significant length, and for also modularity. We need to have a system which is able to be dropped in and provide easy localization in an embedded sense. So the PolyPoint RF localization system itself is based on the concept of a trilateration-based approach. So we have anchors that are situated throughout the environment. Their positions are known. And if a tag wants to know where it is in the location, in the space, it just measures its range to each of these anchors. The intersection of these concentric circles ends up providing its location. But the fact of the matter is, in the construction of the antennas which are used in this in the ultra-wideband domain, there's instances in which one of the anchors can fall within a null of the antenna pattern. So that line of sight path which you're using to measure range might not actually be observable. Therefore, maybe a longer path is observed, which correlates to a longer bias in range, or that secondary path might also not be present as well. Not only do antenna nulls play a role in giving us lower accuracy of these localization estimates, but also if we perform a channel model here, we can actually see that even in the presence of line of sight, we can see large distortions in the ranging error. So on the bottom you can see a histogram across a large number of representative environments. We can see that we can, even in the presence of the line of sight path, which is the one we're interested in, we can see ranging error on the order of a meter or so. So this actually brings us to the point that if we observe large inaccuracies in range, this can lead to large inaccuracies in the actual localization estimate that comes after all of the aggregate. So therefore, we came up with the idea that we would utilize multiple antennas at each of the nodes that's used in the system itself. So we perform 27 different observations of the RF channel, which comes from the utilization of 3 different antennas at the transmitter, 3 different antennas at the anchor, and then 3 different RF channels. But what this buys us is the ability to sample many different points along this distribution, and therefore we find that through channel simulation we can come up with combine these 27 different range estimates and calculate the 12th percentile of the range estimates that were used. And what this actually gives us is the ability to get a better accurate estimate of range. So the median ranging error in this case goes down from the metric of about 17 centimeters down to 8 centimeters, and 95% of ranging estimates goes down from 65 centimeters to 34 centimeters. So it seems like a lot of observations of the RF channel. Are they actually necessary in order to attain this accuracy in practice? So if we're actually going to, so here we actually have 2 nodes which are separated by a distance, and along the y-axis we can actually see the ranging error which is observed based upon every combination of antenna at the node on the left, antenna at the node on the right, and RF channel. So we can actually see that they each have their own characteristic distribution. We ordered them by their median range error, and we can actually see that there's certain instances all the way off to the right where the median error is off the scale, more than a meter. So this actually gives us a good intuition as to why antenna diversity helps us in the worst case. So what happens if we actually move the nodes further apart? One could assume that if we know which antenna channel combination gives us the best estimate, maybe we could just use that again. But unfortunately, the reality of the situation is that the distributions end up changing significantly. So this gives us a rationale for each range estimate that's performed, actually get these range estimates across all these different combinations, even though there are 27 different of them. So how do we actually perform this in practice? So ranging in general is usually performed through the passing of messages back and forth between the 2 different tags. The range is based upon the time of flight over which those, measuring the time of flight over which those packets have spent. So if we look at the time domain representation of this, it starts off with a packet which requires a non-negligible amount of time over the air. There's a turnaround time at the second tag, and then there's a message passed back from the anchor in order to determine range. this turnaround time at the anchor is taken off in post-processing because it is known to the anchor. So if we want to actually determine 27 different range estimates, that's going to naively require the use of 27 different copies of the same message exchange across each combination of antenna at the tag, antenna at the anchor. So what we end up having is, in the case of multiple anchors, which is what we're going to require to perform localization operations, we end up with a large number of packets. So we have these 2 packets per range times the n, which is the number of anchors, and m measurements between each anchor. So in the case of doing these 27 different estimates of range, we end up with 216 packets. So utilizing a sort of metric of about 1 millisecond per packet, this is correlate to about a 5 hertz update rate. So this is actually might be okay in situations in which tags are not fairly stationary across time, but if you're tracking moving anchors, this might not necessarily give you the performance that you require. It also leads to contention on the RF channel in general. So the first enhancement that we use is the leveraging of broadcast transmissions between the tag and the anchors themselves. So instead of performing unicast transmissions between all of the nodes, we instead utilize a broadcast transmission. Then we just have different turnaround times at each of the anchors in order to estimate range. So in the end, the actual 2A time of flight can be calculated in the same way. We keep performing this for each of the 27 different combinations, and this gets us down from 2nm down to n plus 1 times m packets, which is about 135 in our example, which gets us up to a metric of about 7 hertz. This wasn't a significant improvement, but it got us a little bit of the way there. The one thing that we can actually see from here is that these packets back from the anchors are actually somewhat interrelated. So we can actually, in our implementation, we do multiple broadcasts from the tag, and what we can actually see here is that the anchors can determine the difference in range between each of these incoming broadcasts based upon the expected interpacket interval, which is observed. So then we only really need 1 transmission back from each of the tankers back to the original tag. So this gets us down to the order of the n plus m packets, which is 31 in our example, and this gets us up to a much more manageable rate. So not only are there less packets going back and forth, but we're able to achieve higher localization update rate and less contention over the wireless channel itself. So I talked a little bit about how we're able to improve the robustness of this determination of range through leveraging diversity. And this actually has a nice added benefit that we do not require the deployment of as many anchors throughout the environment, because infrastructure is key because of the fact that we're going to have to deploy more infrastructure if we're going to see these ultra-wideband systems deployed in practice. So now I'm going to talk a little bit about how we get around the issue of this regulatory limited transmit power through the use of a flooding primitive, similar to that of the narrowband case, and also how we've implemented a lightweight scheduling and synchronization primitive which allows for multiple tags to interoperate and not interfere with each other during localization operations. So in terms of addressing the scalability, we adopted the low power wireless bus in the ultra-wideband domain. And what the low power wireless bus is, it communicates all data across the network utilizing these glossy floods. There's one specific master node which coordinates time slots for these localization operations. And then incoming tags which want to perform localization operations request a spot in the schedule during a contention period. And then outgoing tags, either if they know they're going to be leaving the schedule, they can request to be leaving that schedule or timed out at a later time. In the steady state operation, all tags are scheduled with an even assignment, a fair assignment of time slots. So I talked about how we actually adopt the low power wireless bus in the ultra-wideband sense, but the low power wireless bus actually relies on the implementation of glossy floods. So in the instance of the narrowband techniques, how a glossy flood works is there's an initiator in the middle, and then all nodes which receive that flood propagate it in the next unit of time, and this continues until all nodes are receive the message in the network. So in the instance of narrowband, it's constructive interference or a constructive addition of sinusoids. That's the equivalent of what it is in the narrowband case. In the ultra-wideband case, it's a little bit different because of the time domain sparsity of the signals which are used. So if we think back to the time domain representation of ultra-wideband signal, it's a pulse, and if we have multiple pulses with some amount of time offset between them, it really just looks like a multipath channel. So if we think about it this way, if we have two nodes which are transmitting the same message, and they're spaced out as shown, it's actually equivalent to a multipath environment because the path lengths are the same, and therefore the channel impulse response will look like a multipath environment in the case of two nodes transmitting with high synchronization accuracy. So this leads us to two necessary conditions to support ultra-wideband flooding. The first one is that of the nodes that are performing the flood need to be synchronized well in time. So if we have any significant time offset between the two nodes that are transmitting, we're going to see significant intersymbol interference, and therefore you're not going to see the effects of the constructive effects of ultra-wideband flooding. So this brings us to our first necessary condition, which is that the transmitter synchronization between all nodes which are performing the flood must be better than the symbol time of the packet which is being transmitted. So the symbol time varies based upon where you are in the packet. During a preamble, it's on the order of a microsecond, but during data demodulation, it's on the order of 128 nanoseconds. So we need to achieve this level of time synchronization in order to make ultra-wideband flooding work. So what we actually see here is that we're able to achieve this 128 nanosecond level time synchronization through a network of 4 different nodes. So what we can actually see here is that the two nodes which are on the bottom have a synchronization offset from the initiating node of only about less than 5 nanoseconds. What happens then is nodes 1 and 2 have now received this message. They propagate the message to nodes 3 and 4, and the time of flight over which that transmission, that flood has propagated, is added on to the synchronization offset. So we end up in this paradigm where the synchronization accuracy between all nodes in the environment, or participating in the flood, is equivalent to the amount of aggregate time spent throughout the flooding. So how it's done in practice is the transmission time of the next flood is based strictly on the received flood timestamp. So there's a second necessary condition, depending upon how the receiver itself is architected, and that is of carrier synchronization. So depending upon how much the phase varies throughout the packet transmission, depending on how the receiver is architected itself, we have to adhere to a strict notion of synchronization in the carrier itself. So this really just brings us to a necessary condition that the transmitters, which are participating in the flood, must maintain this coherence during the packet transmission. And in our instance, this means that our crystals, which are utilized at each of the transmitters, need to be tuned to within 1 part per million. I'll leave a little bit of how that's implemented in practice for further discussion, but that is how we achieve carrier synchronization between all nodes. Finally, I talked a little bit about modularity. So the SurePoint system utilizes a castellated printed circuit board, which has the goal of being integrated in with easily integrated in with a host system. And what this actually does is it provides an abstraction around all of the operations that I had talked about previously. So the module itself is programmable, therefore it could potentially utilize a variety of different localization protocols, and therefore the host system itself doesn't necessarily care how these protocols are done. What it cares about in the end is its determination of position. So therefore we leverage an I2C interface, and there is a dedicated microcontroller on the module itself which performs all this protocol orchestration. We leverage this new commercially available ultra-wideband transceiver, and all that transceiver does is it transmits messages back and forth and calculates the time of arrivals of incoming packets and provides time transmission of outgoing packets. The module is triangular in shape, and this is in order to leverage antenna diversity for the purposes that I discussed previously. So in conclusion, SurePoint was developed with the express condition of overcoming shortfalls of ultra-wideband localization to make deployable systems which target a wide spectrum of potential applications. In the instance of SurePoint, we're able to achieve decimeter level localization accuracy, and we're also able to enable network-wide communication, scheduling, and synchronization through the use of ultra-wideband floods. The TriPoint module, which is the heart of the system itself, provides a localization abstraction, which is a modular architecture and eases the adoption of SurePoint into a host system. And then finally, we're able to achieve high localization accuracy in complex indoor multipath environments, specifically 17 centimeters median 3D error, and 95% of localization estimates are within 76 centimeters. Thank you very much. Do you have any questions?
We have time for some questions.
Here's Daniel from Columbia University. So you say multipath is an issue for you, and of course the time of arrival is going to be the same. But did you look at anything else that maybe changed because of reflection? Like, does the spectrum change, or well, the amplitude for sure? But can that be a cue for you to differentiate if it is a multipath, like, or if a direct path from a second transmitter?
Yes. So that relies mainly on the implementation of the time of arrival algorithm, which is implemented in the decawave transceiver. It's actually a fairly black box approach, so we don't have much introspection into how that algorithm works. But in general, there's a variety of different, if you had access, you could look into the received signal strength, but that also varies based upon a variety of different factors, including antenna gain, how much loss you achieve in the system itself, and a variety of different factors. So that's it is a possible, a future thing or that people have also looked at in the past. Yeah, that's currently how we're implementing it.
Thank you.
Maurizio Bocca, Bosch Research Center. It's a very interesting work. Congratulations. So my question is, you showed that what looks like a Gaussian for the distribution of the channel antenna ranging measurements. Are you sure that that's due to channel antenna diversity? Because what if you take 27 measurements on the same antenna? Could that be also measurement noise?
I just guessed this out of the blue, but this is where I was trying to describe how the distribution actually is fairly stationary, and we can actually see the noise in each of these histograms, or sorry, scatter plots as well. So we actually see that the measurement noise can be attributed to some of the ranging error. Each one of these bar charts shows sort of the measurement noise for any of the antenna-antenna channel pairings, but that can't be attributed to the entire Gaussian distribution that we're seeing.
So my next question would be, basically what you're doing here, you are trading off some of the update rate and scalability of your system for a better accuracy.
Correct.
If I had to, boost a little bit my update rate, should I go for antenna or channel diversity? Because what I see here is the combined effect, but I didn't see, I didn't really understand if it's more the antenna or the channel diversity, especially since you have done measurements only in line of sight. So probably non-line of sight, you would have seen something totally different.
Right. So I would have to say that antenna diversity would be the one to choose among those two, and that for that specific reason that the nulls tend to be correlated in where they are located, even across different channels. We haven't seen any significant correlation between whether or not if you are not in a null, whether or not antenna diversity is better than channel diversity, but I would say for the specific reason of reliability of that line of sight link, because of the intricacies of the antenna pattern, I would have to say that antenna diversity would win out in that trade-off.
And finally, how do you explain these negative ranging errors? I mean, multipath should just increase, right? Should give you a positive one.
Yeah, that's correct. So it's an interesting problem. So this relies on how the line of sight arrival is determined, and utilizing best performing line of sight time of arrival determination algorithms. An example of the best performing today would be one that looks for the 10% height of the first peak of this channel impulse response. So depending upon essentially the phase of the line of sight path versus the non-line of sight path, they can end up in a situation where the magnitude of the channel impulse response aggregated over those two conflicting paths ends up being significantly less, and then that actually translates to a negative shift in the time of arrival if you're doing this normalization, essentially, of the channel impulse response. So that would be my guess as to what Decawave is actually implementing under the hood, but I can't give a specific answer as to why.
Let's thank the speaker again.